you want to protect your IP, which is fine, and you want to protect the investment you're making in innovation. And that's great. We all understand that. We all fully support you. Customers support you. In most cases, people don't want to use design engineers like me and companies that make products don't want to use fake FTDI chips. We want to use the genuine ones. We want to support you. You just need to understand the complexities of the supply chain management and how easy it is for even huge, big, reputable companies to get stung by fake parts. It's just a fact of life that's going to happen. So how about you use this innovation you're talking about to figure out a way how to make your chips lower cost, perhaps, or maybe put some innovation into security, like physical security of the parts, and I don't know, some whiz-bang laser etched graphic on there that's really hard to counterfeit, or something like that. I don't know. You guys are the innovators. I'm sure you can figure it out. And then you tried to cover your tracks. Oh dear, oh dear. In the age of the internet, you deleted all of your Twitter posts to this, responding to people in that aggressive way. It's a good thing I captured those, so you'll see those in the video after this. Fail, really. Oh, and by the way, your intentions weren't really honourable. They were just flat out aggressive and up yours in your face. We didn't like it. That's why the response was so bad. If your drivers simply refused to pop up with a message and refused to talk to the fake chips, hey, that would have been fine. It wouldn't have even made a rumble in the industry. Yet now, my forum alone, just the forum thread, 100,000 views almost, and there's still 100 people live, 150 people live on there chatting about it now. It's crazy. And well, Fred, in the end, we can read right through this bullshit, press release you've got here. It's just, we know that you talk to your lawyers and they come back and say, oh shit, yeah, we might be in trouble. You better not do this. So you've done the right thing. Good on you, and you've taken the driver down, and you admitted you didn't want to have to hurt customers, but you didn't say sorry. It's a pretty piss poor response, I think, and pretty much a textbook example of what we don't want to see. A response, yeah, okay, you pulled it, which is great, but we know you didn't do it willingly. And, where's the remorse? There's none. You read this and it's just like, it's still in your face. You're not going to win back too many pissed off people by doing a response like this. It wasn't heartfelt enough. So whether or not you can salvage your reputation out of this, I don't know. But yeah, it still leaves a bad taste in my mouth. FTDI. No thanks. So anyway, a whole bunch of people wanted to see my original response to this, which I shot last week. It was like Friday afternoon, and I didn't have time to finish editing it, so I didn't get around to updating it. But anyway, here's the original response video I did. And by the way, sorry about that. It's going to be slightly out of focus. You'll see that the focus hunts between my head and the background here, because the Sony Nex VG30 camera that I'm using here, I didn't realize that face tracking that keeps my face in focus here automatically turns off if you choose the manual mode. It's still autofocus is just fine, but it turns off face tracking, which is stupid. I don't understand why I did it. So sorry, yeah, it could be a bit blurry. That's what happened there. Anyway, here's the video. Catch you next time. Hi. Have you heard the one about an EEV blog forum member that walks into a bar and buys a dodgy FTDI chip? Well, if you haven't heard it, there's a huge shitstorm happening at the moment about FTDI chips that are used on all sorts of boards. Let me break it down for you. Now, you should have heard of FTDI chips before. It's that little one there that's used on all sorts of boards to provide a really nice and simple serial interface to a USB port, so that when you design a product like this, whether it be an Arduino or this chip kit or any sort of product whatsoever, if you want to add really easy USB to it and your microcontroller's got a serial interface, the FTDI chip is the chip of choice to do this. It's so massively popular in the industry, and they're not particularly cheap, and this is why there is a huge clone market out there for fake counterfeit FTDI chips. They're not they work right? They're perfectly fine, but they're just not genuine FTDI chips. They've actually ripped off FTDI and they don't get any income from them. And, well, that's not nice, but hey, it's not uncommon in the chip industry. So anyway, an EUV blog forum member the other day, NCT Nico, posted that he had a board that he bought off eBay and it had an FTDI chip on it, and he plugged it into his Linux machine and it worked just fine. And then he plugged it into a Windows machine and Windows automatically updated the driver software, the FTDI driver software. It detected that the chip was an FTDI chip and installed and updated the drivers. And then what happens? What? The board fails, and he puts it back on the Linux machine and it still failed again. So what's happened is that FTDI have recently updated their drivers, which then automatically get downloaded via Windows and updated when you plug in a board, any board that uses either a fake or a real FTDI chip. So what's changed in these new drivers that's created all this furor and anger towards it? Well, what happens is if you plug in, or when you plug in a board, it detects whether or not the chip is a real FTDI chip or a fake one. And if it's a fake one, it rewrites the product ID, the PID code, to 0. And because the PID code is stored in E2PROM inside the FTDI chip itself, it doesn't matter whether if you remove power and plug it back in, if that PID code is 0, then Windows or Linux or other operating systems cannot read this chip, and you've effectively bricked it. What? Because inside these types of USB chips, they contain a vendor ID and a product ID, and the Windows and other operating systems use those two codes to determine what driver needs to automatically install. So if you're used to having something plug in and bingo automatically detects and installs drivers for you, that's how it's done. But if that PID, that product ID code is 0, the operating system just goes, no, I have no clue, I'm not going to use that chip at all. And it's effectively useless. They've bricked your board. Unbelievable. But surely this has to be some misunderstanding, right? A company like this is not going to go out and deliberately write code that bricks products like this. Surely not. They can't be that monumentally stupid, right? Right? Yep, you guessed it. They are deliberately, willfully, knowingly doing this. They are now deliberately bricking products like this if they contain a fake FTDI chip. Oh, double facepalm. So anyway, this forum post turned into a Hackaday post, which then got reddited and slashdotted, and it made its way into all of the major, tech blogs and things like that, and it's just massive. I was getting like over 5,000 views in the forum thread when it was posted. Absolutely incredible response from this, and everyone is up in arms about it. And here's why. This is FTDI's only official response that I'm aware of so far was on Twitter. So Mike from Mike's Electric Stuff asked the first question of FTDI and posted a link to the forum article. And this is FTDI's response to all the criticism that they're deliberately and willfully doing this. Here it is. We recommend that to guarantee genuine FTDI products, please purchase either from FTDI directly or an authorized distributor. And after that, Jim, they posted this Bobby Dazzler. Please refer to FTDI's driver license agreement. By installing FTDI drivers, you agree to the terms of use of FTDI's devices. So what they've basically done there is admitted that they're doing this deliberately as part of a deliberate strategy on their part, and they're saying, well, screw you if you don't like it. Well, FTDI, you're the one who's going to be screwed. And yet, FTDI kept digging their own grave. Mike then responded with, breaking people's stuff without warning is unacceptable. And FTDI's fabulous community response to that. So are counterfeit ICs. They're destroying innovation in the industry. Please ensure genuine ICs before using FTDI drivers. Another screw you if you don't like it. We're going to deliberately brick your product. Too bad. So you just got to wonder, what dickhead at FTDI thought this was a good idea to deliberately write some code, put it in the drivers, sneak it in there, and then just say, oh, too bad, if you don't like it, read the terms and conditions, and then deliberately brick people's products. People who might have innocently bought a product, they had no idea about an FTDI product. Even genuine manufacturers who specify in your parts, and through an accident in the supply chain happen to end up with fake chips, and you're going to brick them? Unbelievable. It is the absolute worst possible and stupid corporate destroying move you could possibly do. Oh. And then David Blay on Twitter writes, reprogramming fake chips does not hurt the counterfeiter. They have already sold the part. It hurts the FTDI brand. And FTDI's brilliant response to this, because they do it so well so far, it means counterfeiters don't exploit engineering investments made by FTDI, hence ensuring your source is key, i.e. where you source your components from. So FTDI don't give a shit about their brand. Unbelievable. So this is obviously, some dickhead there has obviously determined that this is beating the counterfeiters in this method, the most brutal way possible that harms almost everyone in the chain, is more important than their brand. Unbelievable. And FTDI's final word on this whole saga: sadly, protection against counterfeiting is a growing issue. If you have ideas, we'd be interested to hear more. You bet we've got some bloody ideas, dickheads. And first of all, the idiots at FTDI clearly have no clue about how the real world works, supply chain engineering, design and manufacturing and things like that. They seem to think that the solution is not just buy a genuine FTDI chip and that's the end of it, right? What's the problem? It's your fault if you buy a fake chip. Well, that's not how the real world works. When an engineer like me specifies an FTDI chip, designs it into the product and specifies that in the bill of materials, then, well, it's out of my hands. Then it goes on to the manufacturing department, the purchasing department, to actually purchase these products. And supply chain management is a huge, big beast in its own right. And often you can't get parts; they're not in stock from either FTDI themselves. I've personally had issues trying to get FTDI parts, which they recommend just buy them from us, hey, or from the authorised distributors. They might be out of stock, because at any time somebody can come along and buy all the DigiKey and Mouser stock, all the stock in the world of that particular FTDI part, and you're screwed. So what do? You try and shop around for other FTDI chips, and you think, you go to a reputable supplier you've used before, and they said, yeah, these are genuine FTDI chips, but it turns out that they're not, because they've sourced them from somewhere. There's so many. All it takes is one slip up of anyone in the entire supply chain, not only at the company who's manufacturing these things, but just anyone down the chain. Everyone relies on everyone else, and it's so easy for fake parts like this to slip in. Even huge companies get caught out with fake parts like this. It happens all the time. So by you now admitting that you are deliberately bricking products like this if it uses a fake chip, I hope you've got a good team of lawyers, because all it's going to take is for one big corporation, for somebody in that chain that I talked about slips up and they ship 1 million boards and your driver software automatically bricks them all. Wow. Corporate suicide. You're going to go out of business. Not to mention that doing this has just completely destroyed your reputation. I'm not going to design FTDI chips into my products anymore, and a lot of people are saying the same thing. And you are the #1 in the industry for USB driver chips, and you just completely thrown it all away. It's monumentally stupid. So it's just a matter of time before a big engineering company gets bitten by this, and well, geez, you're not going to win. You're going to go out of business. Congratulations. After all, you've deliberately and knowingly put code in there that destroys these chips. And well, no, it's okay. Granted, you can actually recover these, but it's not a simple process to actually do it. So for all intents and purposes, especially for the end user who's using the product, the thing is going to be essentially bricked and becomes useless. So a big name company can completely lose their reputation as having a crap product when it was just an innocent fault of one little person in the supply chain, and it's going to be all your fault, and you've publicly admitted that you actually do this. And somebody on the EEB log forum even disassembled your code, and sure enough, there we go, it deliberately does it. It's even in your terms and conditions, which of course nobody bloody well reads anyway, but when these things are automatically pushed out via Windows Update, oh man, fail. And anyway, apparently Microsoft are not happy about this, and they're sort of starting to wave the finger a bit and saying, hey, what's going on here? This could be a big deal. But hey, you asked, what can we do about it? If you've got any ideas, let us know. Well, just off the top of my head, stop doing this batshit crazy, worst possible thing you can do. It's going to ruin your company, you idiots. Not that I care. I'm not using FTDI anymore anyway. Idiots. There's obviously several ways you can go about this. The simplest is just simply having your drivers refuse to work if it detects a fake FTDI chip. It's not rocket science. Jeez. And that doesn't hurt anyone. You're not going to get your ass sued off, and you're not going to lose your reputation. It's just a no-brainer. Other things you could do, well, you could pop up with a big message saying, hey, this is a fake FTDI chip, and, really give a nice, detailed and a good explanation of why, buying or designing in fake FTDI chips is a bad thing. Talk to the engineers out there like me who know these things and are going to design these parts in, and inform who can then inform the purchasing people and so on and so on down the supply chain. Don't destroy, educate. And you can maybe even link to a video showing why the fake FTDI chips are, could be potentially bad in a product like this, and how the user should let the customer, the manufacturer, know that they're using a fake FTDI chip. And hey, it hurts the industry. We get it, okay? Counterfeits like these are bad. We understand. We've taken the worst possible response, which is damaging everyone, including yourself. It's just ridiculous. So this is no way to beat the counterfeiters. You're just going to beat yourself to death with a stupid stick. And if you're really nice, you can even pop up with that message, as I said, but still allow people to program and use your drivers with those FTDI chips. It might pop up with an egg message, or it might, inform them, might program it slowly, it might do, I don't know, it might do something, right? But it still at least lets people use the thing. But hey, almost, I'm sure everyone would be happy with you simply refusing to talk to a fake FTDI chip. That's just fine. And I'm sure other users will voice their opinions too. Just read the comments in the video and all the other articles out there. I'm sure you've already gone into crisis mode and going, oh, what happened here? Oh, we didn't expect this. Well, bloody hell, what did you expect? So the idiot that approved this should get their ass kicked right out the door and down the street to an unemploymentville. Still can't get over this. This is just so massively stupid. It is. Hi, welcome to a teardown and potentially maybe the first part of a repair video. Check out what we've got. We've got an Agilent, it has actually Agilent on the front, N8762A system DC power supply, and this thing is a beast. Check it out. Look at the specs. Woo, baby. 600 volts, 8.5 amps, 5100 watts. Wow. In a 2-rack unit high thing. This thing is an absolute beast. I got it courtesy of Charles at Trio Test and Measure, and he got this from a customer. They blew the arse out of it. They released the magic smoke, and they were going to toss it in the dumpster, I believe. So Charles saved it, and he said, here, we can have a look at it, have a teardown, and maybe have a repair of this thing if we can. Anyway, so let's take a look inside. Oh, it's a Bobby Dazzler. Look at it. I mean, voltage and current, like a lot of these system power supplies are just that. They're designed to go into racks, into systems which are under PC control and things like that. But this puppy has the rotary encoders on the front for the voltage and current control as well, and limiting and all sorts of stuff on the front. Very handy for control. I hate the system power supplies that don't have any front panel indicators at all. It's just annoying. And this particular series of system DC supplies comes in many different models, of course, as is common for these type of things. Anywhere from an 8-volt unit with 400 amps capability up to the highest voltage model we've got here, 600 volts at 8.5 amps, 5100 watts. And yes, 5100 watts is more than your average PowerPoint can supply. So 240 volt or 110 volt, 2400 watts here in Australia is the maximum. So it's 5100. So yes, it is 3-phase. And the specs are incredible too. This is a 0.025% basic DC voltage class instrument, 0.1% on current. Absolutely incredible for such a high voltage, high current unit. Tell us the price, son. Well, this particular model, 7,700 Australian dollars ticket price. Crikey. And on the back here, we've got good old school GPIB. We've got 10100 Ethernet LAN. We've got USB host. We've got inactive, whatever that is, out in, I don't know, some sort of control thing. Maybe we've got a cat on here. That's the remote programming interface. We've got some dip switches to set some various things. We've got the sense lines. Yes, you've got at these sort of currents, you've got to have 4-terminal remote sensing, and here's our voltage output. There's a big ass terminal block there, and there's actually 2 connections for the positive and 2 connections for the negative. So if you want the sense line, if you want to sense it at the load, then you've got to take it from here. But as you can see, as is quite common, if you're just using it basically without any sense, then you just put in loop back pins in there to do local sense feedback. And here's the trick and why it released the magic smoke.
here's the three-phase inputs, right? So you've got L1, L2, L3, plus your earth terminal, okay, no problem. Standard three-phase input, 190 to 240 volts, okay. Yep, it's designed for the Australian market. Look, up here, 190, 240 volts AC, 3 kilowatts plus, no worries, right? Wrong. This one's actually a 120 volt US model because we're talking three-phase, and in a Y arrangement, that can be 208 volts, or it can be 240 volts, depending on the particular configuration for on per phase for a 120 volt nominal country like in the US. There are various standards, and I won't go into them. It depends on what type of factory and installation and what type of three-phase system, how it's wired, etc., etc. We won't go into it, but basically, no, you could be fooled into thinking this is a 240 volt unit, and you can hook it up in a country like Australia, which is a 240 volt country, and you can hook it up to our three-phase system here, but you can't. Here, it's actually 400 volts for a three-phase system typically. So that's exactly what they did here. I don't know where they got this thing from. I don't know the history, but Charles tells me that sure enough, they actually hooked this puppy up to a local three-phase system here, and the magic smoke escaped. Awesome. Let's take a look inside. So let that be a lesson to you on three-phase systems. Know exactly what you're doing. Don't be fooled by labels like this. But yes, even though I don't have three-phase here in the lab, I could actually technically hook this up to a regular 240 volt outlet. I could, there's no reason why I can't feed my single-phase 240 volts into and parallel it on all three inputs like that. It's just that I wouldn't get the available power, of course. I wouldn't get the full 5,800 watts that this puppy is capable of. But, hey, it still allows me to troubleshoot and do everything else. Actually, technically, I would not do that here in the lab because my lab voltage here is actually 245 volts at the power point. And actually, I'll prove that. And there you go. I'm actually pretty close to 247. So that's really at almost the extreme limit of what they're allowed to actually give us here. So, yeah, not necessarily such a good thing. So even though it's only 7 volts over the nominal operating limit of 240 volts here, and it'd probably work, I'd be incredibly surprised if it was an issue. Still, just as a matter of course, you wouldn't do it. So I would use my, in troubleshooting this thing, I would use my adjustable mains power supply. So here we go, let's pop the lid on this puppy, and this thing is going to be first class. I can guarantee it. They will have spared no expense on the parts, and the construction will likely be absolutely drop-dead gorgeous. Let's hope. Agilent, don't let us down. Sorry, Keysight. Does have Agilent badge on the front though, sorry. Oh yeah, baby, look at that. That is gorgeous. Wow. And even though this puppy has been powered off for a long time, and I'm sure it's got bleeder resistors in there, not to store any residual charge on the caps, when you're fucking around with something like this, you just want to check first. So I'll get in here to this lovely looking bus bar, and I'll give that a probe, and yeah, bugger all, and then you can go probe the main side, but it's all discharged. You just want to make sure this whole thing is discharged, both the secondary high voltage DC side and the primary side over here, all discharged before you go poking around in here. And just remember, if you want to discharge some things, if you've got a multimeter with, ta-da, one of those low Z things, then, well, that'll do the business. It'll put a resistor in series, in parallel with the series, parallel with the cap, and it will discharge it. So, and it'll display the voltage as it discharges. Beauty. Now, first thing I'm going to do is give it an old sniff test. No, I can't smell anything really hurt. So, yeah, and visually, at first glance, I don't see anything wrong with this thing at all. I can see, yep, down here. Well, it's not actually something wrong that's blowing up, but two of the fuses for two of the phases here are missing. These are look, 30 amp big beast HRC ones too. 30 amps, 250 volt rated fuse. They're missing. So I don't know whether or not somebody's had a go at this thing, or whether or not the fuses just blew out. I mean, look, there's something happened there. Perhaps that's yes, actually. You see, in the side of these caps here, look at all that. There's all this crud. I mean, this is a very clean unit. This crud is not anywhere else. It's not dust or anything like that. So it looks like, this fuse here is likely like totally exploded. And yeah, all the crap and it's just, yeah, it's not charred everywhere, but it's, yeah, I don't know. Has the ceramic exploded? I don't know, but I mean, HRC fuses are supposed to take huge surge currents like that. So I'm surprised I can't immediately see anything else visually glowing in this thing. That's funny looking. Check out that. They've got some silicon stuff on one side of this cap here. Are you kidding me? Like, why? It's no, it hasn't like oozed out of the bottom of something. I'm actually can see this actually in quite a few places around in here, actually gluing components together. But why they've just stuck it on the side of there, I have no idea. Because they haven't done that to these ones down here, so go figure. And just look inside this thing, isn't it gorgeous? All separate door construction. Here's the mains input here. It's going to have, it's actually got, there's a big plug-in switch on the front, but this is going down to there, so it looks like it might have some relay switching to actually turn that off and on, even though it's got a big plug-in switch. It doesn't seem to be, it's certainly not switching the three-phase, the actual mains input, so it's doing that electronically. And we've got, I'll show you inside in a minute, we've got three big-ass bridge rectifiers here, so see, three separate fuses. We've got some caps, we've got our common mode chokes here, so we've got three-phase common mode choke arrangement. We've got our three bridge rectifiers here, and I assume these the big-ass relays, that looks like a little transformer. We'll have to get some numbers off those puppies. Anyway, it's got power factor correction as well, so it's going to be doing some power factor corrections at now on this board here. And then these are our two big output boards. Even though this is only a single output, it's obviously getting like this is like the highest power model available. So they're obviously paralleling two of them. You can see that on the bus bar arrangement here. These are the two outputs here of the supply. These two here. See, I can touch that because I've already measured it. The two outputs here and the two outputs here, these are identical power supplies. They just put them in parallel, these huge bus bars, and then these bus bars, it's quite nice, they come up into this top board here. You'll notice they removed some of the solder mask to increase the current handling capability of the copper on there, but that's probably a 2-ounce copper board anyway. And it just go into the output terminals here. Whoa, nice little spark gap in there. Let me show you. There we go. It's always nice to see a little spark gap arrangement like that. I've done a video actually arcing these across, and it's really cool. I'll link it in if I remember. And no wonder this thing is gorgeous. Well, it'll be gorgeous anyway, because Agilent/Keysight know how to design products, and they design really good ones. But the best in the business has done this. TDK Lambda, well, one of the best, if not potentially the best power supply manufacturer in the world. So it looks like Keysight have Agilent subcontracted TDK Lambda. No surprise. I mean, leave it up to the experts to do these sort of things. And they would have charged a pretty penny too, let me tell you. So it looks like every power supply board in here is TDK Lambda. This one is, this one, and your two main power supply outputs as well. So it looks like Keysight have subcontracted out that. Probably, maybe this output board here might be, custom Keysight, and maybe, the digital side of things, that wouldn't be TDK Lambda, that'd be all Agilent. So we've got GPIB board here and processor, and it looks like a control board down the bottom. And it looks like someone in production has written some stuff on here after testing. What is that, P200 5K? So is that maybe 5 kilowatts? They tested this puppy at 200 volts, maybe. So yeah, they've written those on top of the heat sinks after they've done some production stress testing on this. Sorry for the handheld footage, but it's the easiest way to get this. Yeah, here's one of the relays on the main power supply input, Tyco relay. I'm not going to look up that number, but it certainly is. And there's two of those relays in there, that one and that one. And as I thought, this one is a transformer, so that's doing some, tapping off a signal for sense or something like that. Now, one thing I'm a bit disappointed at, just from a service and teardown troubleshooting point of view, is that, they've labelled all the connectors, CM1 and everything else, but why can't they just label them with their system function, 5-volt rail, 15-volt rail, whatever, actually be more descriptive on the connector outputs. But there's nothing like that on here. There's no test point voltages or anything like that. So, it's not exactly service friendly, and I can't, I had a quick look, but I cannot find the service or service manual or schematic for this thing. So if anyone has it, please leave it in the comments, because that would be absolutely fascinating. We'd be able to tell a lot more without having to reverse engineer all this jazz. But what I think, we've got our input, mains input switching here. This looks like our, as I said, the power factor correction. That's important when you're talking about these sort of loads, or your professional power supply is going to have PFC in it. It looks like we've got another power supply board over here, which looks like it does the low voltage rails for your digital and stuff like that, and our secondaries. Actually, this PFC board here has the older Mimic Lander name on it, and that's the same as the mains input as well, but the low voltage DC supply has TDK Lambda, as do the two main power output ones as well. They're also TDK Lambda. So yeah, maybe a different group within Lambda. Lambda, the Tri-Lambs. Yeah, 80s aficionados will get that one. And of course, you expect nothing less than Nippon Chemicon. There you go, the real deal. 105 degrees C, of course. So, of course, these are all Nippon Chemicon, all the major ones in the DC power supply and the input, the output side and the input side as well. And they've put that grey Celastic in between those to stop them flapping around in the breeze. Don't want them vibrating. Nothing worse than vibrating capacitors. Really annoying. So those caps are the output side, of course. They are, of course, 450 volts. So this is a 600 volt capable supply. So they're going to have those puppies in series. So they'd be series. So they'd be two in series and then two in parallel, like that. So two groups in parallel. The output diodes here, we've got 8 of those on this directly tied to the bus bar output. And there, see, because they've got no insulating washer, no seal pad on the back of that. So they've got, 4 on one side, 4 on the other, feeding the direct rail, which goes right out there. Right to the bus bar. Very nice. And then there's our primary side switching transistors. We've got 4 of them down in there. They'd be big ass MOSFETs, big seal pad on the back of that. Don't need too much heat sinking on there. This is a pretty efficient design, but as you can see, they've got the fans right here, so driving the air directly over these. The heat sinks are oriented in the correct orientation, except it sort of would have been nice to put this in the path of the fan here instead of just slightly outside the path of it there. It would have been nice to get that air going over the fins, but they've done their homework, they've done their testing, and that's adequate. So that's small, air being sucked in the front and pushed right out the back, directly across all of these. Would have been a real faux pas if they mounted the heatsink like that orientation and then just blocking all the air. That's a trap for young players, that one. And you can see that they've done this absolutely perfectly designed up on the power factor correction board up here. They've got the fan here. It's sucking the air in from the front, blowing straight over the capacitors first. So it's keeping those really cool. And then the two heat sinks are aligned in the correct orientation so that the air can flow over the fins and straight out. So it's if you had it the other way, so that these capacitors were on, over here, like this, then you'd be blowing the hot air onto the capacitors, and that's not good for their life. So you want these caps on the cool side of the heatsink and the airflow like that. Nicely designed. And they've got themselves a little temperature sensor there right on the heatsink. That's very nice. That's a Token brand. NEC own those, I think, or buy something, I don't know. Anyway, it's a little NEC Token temperature sensor. very nice, directly sensing the primary side output heatsink. You can see here that the secondary side, in addition to the 4 other diodes on the other side of the bus bar here, there's addition for another 4 in there, so that would be for a higher current model. And I think you can see down there, there's a jumper in one position there, and that would be to configure these output capacitors in series or parallel combination for, once again, for the different voltage current models. So lower voltage model, they might whack all these, and higher current, they would whack all of these 4 capacitors in parallel, whereas the higher voltage one like this, the 600 volt one, they would actually whack them, well, as I believe, I think they are 2 in parallel, and then that group in series with that group to get a higher voltage. And they probably have a ballast resistor on there, I'd be guessing, just to equalize the voltage across the 2 of those. Well, looky what we have here. There we go. There's where our magic smoke escaped from. Looks like we have, is that a moth? We've had the arse blown out of that one. Only one of them. Only one. So, yeah, that's interesting. That looks like the only visibly damaged component in this thing is C, where it's just blasted. Look, it's blasted right out here and just spewed all its guts right against this heatsink. So, yeah, that's the first thing you need to fix. And that puppy's actually a Nippon Chemicon mod. That's 470 volt nominal rating, hence the 471K there. That's a dead giveaway. And this one's a 30 joule job, so it's a bit beefy, but yeah, obviously, because you plugged in 400 volts AC in here when you rectify that. Oopsie! Now, just looking at the failure mode here, we know we put 400 volts per phase onto this puppy. So when you full wave bridge rectify that, of course, you're going to convert it to DC, multiply that by 1.41 times, and it's going to jump over here via these big jumper cables I didn't show. It's going to jump over this power factor correction circuit, and so like we've got a little mold down here which is blowing on this side, but it's only for the low energy stuff going over to this secondary one. So yeah, so that's not like a main mod. I don't think it looks like. I might have to get the board out to check the wiring. It doesn't look like it. That doesn't look like it's huge directly in the path, but it's still there and it blew. But anyway, you would suspect something on here. I mean, your DC filter caps, we've only got 400 volt caps, 420 volt rated caps there on our main DC rectified output of this thing. So because we're basically full wave rectifying the mains input. So that is not high enough rating to cater for the 400 volts per phase that we got here. But there looks to be no stress damage to those caps. But I wouldn't probably fix this thing without replacing those and putting it back into a production environment or something like that, perhaps. But anyway, there's no physical stress on those. There doesn't look to be any physical stress on any other parts in here. None of the 4 transistors in here have any blowholes or signs of physical stress. But yeah, we don't necessarily know that. But visually, the only thing I can find is that MOV. Now, in theory, because the main output of these DC caps, if it stresses these ones, then it's going to stress these ones up here as well on the input. Because there, we've got our wires coming here, they go straight over to the input. They've got the same caps here over here. So they're effectively parallel, but they're like doing some local bulk storage down here for the channel. So, these ones could have been stressed as well. But yeah, I can't see anything at all. But after that, I mean, I wouldn't expect anything on the secondary side over here to be blowing. So if anything's going to be blowing, it's the primary side over here and all this power factor correction stuff in here. So who knows, we might have got lucky and the fuses here and the MOVs actually protected, or MOV, singular, well, the others would have kicked in as well, but they didn't have their arse blown out of them, so all the energy was directed to that middle one by the looks of it. But yeah, they could have taken out the fuses quick smart before before the energy could build up in these caps here, and well, that's where, and damage anything else. That's what you'd be hoping anyway. This puppy's interesting. Check it out. A little transformer there that's got this big ass like secondary winding here with like a coiled, a wrapped like sense wire around that, just going on the secondary side there. It's got 4 pins, but it doesn't look like there's any coil on the second side there, only on the primary side here. And they've got a similar sort of thing happening there on the output board. Look at that. That puppy is just flapping around in the breeze there. Not sure why they've done that. They pop the main output board here. You can have a look at it. Look at these big, once again, the same Nippon Chemicon, the same series. These are big 450 volt caps, and they've whacked these in series because this is a 600 volt power supply. You can see they've actually circled 600 volt on here, and these 4 resistors here, these would be the ballast resistors that ensure that the voltage is shared equally between these 2 caps here. I mean, you can actually rely on the caps to self-balance, but, using the internal ESR, but yeah, that's a bit how you're doing. So, you can see that they've done it properly and put in the proper ballast resistors, and they've even got them stood off from the board there. Lots of air spacing under there, no wuckers. We've got ourselves 4 sets of suppression caps here, and they're celestic together, no worries whatsoever. And that's it. That looks like a common mode choke. It's not very impressive. It's only got a single turn on each side there. So, but anyway, that common mode choke is actually so that's what they've got. The spark gaps across the common mode choke there. Now this is really interesting. Check this out. There's a big ass bridge rectifier here on the output board. Now, is it actually doing any bridge rectification? Well, let's follow the money and see what we're doing. This is the positive pin here. Okay, the 2 middle ones, you can see they're the AC input, and the negative pin is over here. Let's take a look at this positive pin. The positive pin here is connected to this terminal here, which is, I've actually traced out, this is actually the negative output terminal. Okay, so the negative output terminal to the positive pin of the bridge rectifier. Look at these 2 AC input pins. They're going nowhere. They're flapping around in the breeze, and I've actually confirmed on the top, you may not be able to see that, but I've confirmed that those pins actually go nowhere, okay? So they're completely isolated, and then the negative terminal of the bridge rectifier is going over to here, to our negative output, right over here to our negative output terminal here. What's going on? Let's go to DaveCat. So what they're doing here, here's the negative output terminal on the back, and they're actually basically putting 2 series diodes like this in, and then 2 of those in parallel, because these AC terminals here are just floating, okay? They're not connected to anything. So you basically got 2 diodes in series, 2 in series, and then those in parallel going down to the negative terminal of your power supply output. So, yeah, all of the output current is flowing through this diode bridge. Why they're doing that in the negative line like that? I don't know, some sort of sense thing, reverse protection somehow. And it doesn't actually make sense until you have a look at the second part here, which looks like another 4-terminal bridge rectifier, but it's not. It's actually a high-value 4-terminal current shunt resistor. Aha, let's go back to DaveCat. And bingo, our sense resistor is in parallel with the diode bridge here. So this is our output current sense resistor. They're doing low side current sensing. It's 4-terminal, of course, to get the accuracy, because this thing's like 0.1% accurate on the current over the full range, I believe. So yeah, so that's going, this sense terminal is going off to a connector, which is then going back down to the board, and then measuring that with a diff amp is not on this output board. It's actually back on the main board, so that's a bit doing almost. I like that. I like having my differential sensor